Okay, so what just happened there? You had a balloon. Now, remember, here's the details on this. So, the balloon has air molecules in it. And what they're doing, when they're moving around, they're squeezing against each other and bumping and stuff. They're also bumping against the inside of the balloon, right? And they're pushing it out and trying to get it to expand. And there's also the balloon itself got the rubber that's trying to contract. So there's that force. But there's also the force of the atmosphere pushing inward of the air molecules that are outside of the balloon, bumping into it and just basically running into it on a super duper 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 submicroscopic scale, right? And the thing is, this atmospheric pressure, every square inch of that balloon surface is being hit by 14.7 pounds per square inch. Every square inch is hit by 14.7 pounds of pressure. Now, the reason it doesn't go flying off is because this side's being hit by the same amount of pressure, and so is this, and so this, and so is this, so is this. So we don't see it. It kind of neutralizes itself. It's balanced. It's in a state of equilibrium that it's being hit equally on all parts of its on each side. So no real direction. Now, if you blow on it to make the balloon move, that puts a little bit more pressure here, and that's going to make it move. Because basically, remember what I said, that pressure moves from high pressure to low pressure. Okay, that's kind of the rule. So if you have this side has the higher pressure and this side has the lower pressure, this side's going to be pushing harder, so it's going to move that way if you blow on the balloon. Or if you take away some of these molecules that are hitting from the outside by putting it inside of a bell jar, inside of that vacuum chamber, and you remove some of the pressure on the outside, then this is going to be higher than that, which means it's going to grow, it's going to expand. That's why the balloon got bigger, right? Because pressure always moves from high pressure to low pressure, and if you reduce the pressure out here, that's going to expand the pressure there. Okay, so anyway, that's an interesting thing. Now, another way you can do this is, what if you had like a soda pop can? Okay. Now, a soda pop can, made of aluminum or whatever, it's got air on the inside and air on the outside, and all the air molecules are bumping against the surface of it, and they kind of balance each other out. You don't really notice it. Because, it's got 14.7 that way and 14.7 that way. But here's what happens. If you heat it up on a fire and you put a little bit of water in there and it boils the water, then this steam will fill the soda pop can and all the air will be pushed out. So now you have really high temperature steam hitting the inside here, and so it's hitting really hard, but there's fewer molecules than what's hitting here, but it still equals out, right? Because if it doesn't equal, it's the air will just leave. But if you quickly cool it down by putting it on ice and you make it so the air can't come back in, then the outside pressure is going to be greater than the inside pressure, and it always moves from high to low, and so it will collapse. It's called like a collapse the can kind of thing. Now, I have a couple of videos I'm going to show you that. And when we get back in school, maybe we could do it live with some soda pop cans. That would be kind of fun. I'm kind of hoping to. So, anyway, check this out.